We have two specific types of lines that we want to discuss as we continue to build towards this definition of what a derivative is. So we want to start with a secant line. A secant line excuse me, is a line that passes through any 2 points on a graph. So we can choose any two starting points. And we could draw a straight line connecting them. So this straight line, wherever we draw it, again, if we chose a different point, if we looked at x equals 500 instead of x equals 800, obviously we're going to end up with a different slope depending on where we choose that second point to be. So in order to calculate the slope of a secant line, we're going to, again, just come back to that basic equation for the slope of a line. So this first point that we plotted is the point a plus h, comma, f of a plus h. So again, with this notation, keep in mind that this value a is just whatever our initial value is for x. So in this case, it was at 100. And then h is just the distance between those two x values. So we started at a, and then we add h to it, which brings us to this point, a plus h. So our x-coordinate is a plus h here, and then we plug that value for x into our function, which gives us a function value of a plus h. Similarly, we could define our first point to be a, and then our function value at a. So we have 2 points on a straight line, meaning we can calculate the slope of our line as f of a plus h minus f of a over a plus h minus a. And in this case, again, the denominator is going to simplify. A minus a will cancel out, leaving us with just that h in the denominator. So when we find the slope of the secant line, this is the exact same idea as average rate of change. So when we talk about average rate of change, when we talk about finding the slope of the secant line, those two ideas are essentially the same thing. So we can talk about secant lines. We can also talk about tangent lines or finding the slope of a graph. So the slope of a graph at some point a f of a can be calculated as, and if we introduce a few points here to demonstrate this idea. So again, we're considering an initial point, a comma f of a. Sorry about that. And then we're choosing some second point on our graph, which again, there's some distance h between those two x values. So now what we want to do is again consider that distance between our x values to be approaching 0. So we want the distance between these points to be getting smaller and smaller and smaller until these 2 points are essentially on top of each other. So whereas we would have started with a secant line passing through these 2 points, as that second point keeps getting closer and closer and closer, our secant line continues to change until we have what we call the tangent line. So a straight line that just glances off our graph at that point, at that initial x value. So that's what we mean by the tangent line. We take that secant line, which would be the distance between 2 points, and we make the distance between those points smaller and smaller and smaller and smaller until we get a straight line that just glances off our graph at that individual point. So we can evaluate the slope of our graph or the slope of our tangent line as the limit as h approaches 0 of f of a plus h minus f of a over h, if that limit exists. And again, we saw this just a minute ago. This is exactly the same thing as instantaneous rate of change. So again, both of these ideas, average rate of change, instantaneous rate of change, slope of our secant line, slope of our tangent line, come back to this idea that's really based around just finding the slope of a straight line. This gets a little more complicated, though, with graphs. Since our graph is changing directions, the slope is increasing, decreasing at different places. It's not as simple as just choosing 2 points and applying the slope definition as it is. We have to consider this limit-based definition for finding that instantaneous rate of change.